Hello, my name is Bruno Berenguel and I'm going to present our paper Scaled 360 Layouts Revisiting Non-Central Panoramas. In our paper, we aim to recover a scaled layout from a single image. The layout of an indoor environment is an attractive tool for different applications, as virtual or augmented reality, object segmentation, or even navigation. There are many different approaches for layout recovery. However, we focus on layout recovery from single panoramas. Here, we show two examples of our proposed method, where scaled layout has been recovered from the corresponding panoramas without extra measurements. We compare our proposal with the main state-of-the-art works. Corners for Layouts propose a convolutional network with convolutions adapted to the spherical distortion of equirectangular panoramas, obtaining the boundaries of the structural lines and corners of an indoor environment. HorizonNet proposes a different architecture, combining a convolutional feature extractor with a recurrent block to obtain 1D representations of the boundaries of the structural lines. AtlantaNet proposes a similar architecture as HorizonNet, however, they are able to also manage Atlanta environments. These works provide enough information to recover up to scale layouts linked with some extra measurements, as the camera or the room height. We propose a new method to solve all the cases presented and compute the scale directly from the image information without any extra measurement. To achieve our goal, we propose to revisit the non-central panoramas. A non-central panorama can be modeled as the projection of the environment into a toroidal surface. The optical center is distributed in a circle of fixed radius. Each optical center presents a region where the projection is locally central, which corresponds with a column in the image. These panoramas provide 360 information of the environment, and the image distortion of non-central acquisition system includes subtle differences, allowing geometric 3D reasoning. However, due to the complex geometric modeling and sensitivity to noise, it has been little used. We propose a new pipeline that combines deep learning and geometric reasoning. We propose a network architecture similar as HorizonNet. Due to the recurrent block, the network learns to extract the boundaries of the structural lines column by column, which fits perfectly and is very suitable to extract the structural lines from non-central panoramas. The network also imposes some restrictions, as horizontally oriented panoramas. We turn these restrictions into an advantage, using this information as prior in our geometrical processing. Then, from the output of the network, we propose a geometrical processing that exploits the properties of non-central panoramas to compute the scaled 3D lines. From our geometrical processing, we assume that man-made environments are usually built by vertical walls that intersect the ceiling and the floor in two horizontal parallel straight lines. In our first approach, we propose a DLT-like solution for independent wall extraction. Taking more than 3 projecting rays for each wall, and with the parameterization of the walls as seen in the figure, we can build a linear system that usually computes the wall direction, room and camera heights and wall locations. Obtaining a first estimation of all the walls' direction, we propose two solutions to only obtain the whole layout assuming Manhattan or Atlanta world. For Manhattan environments, we cluster and label the walls in the two main directions. Assuming that all the walls share the ceiling and floor heights, we extend the DLT-like approach to fit all the walls. For the Atlanta environments, since all the walls can have different horizontal directions, we need another approach. Assuming the walls' directions are known, we must ensure that the ceiling and floor height are common. For that purpose, we propose a solution building a linear system where the projecting rays are expressed in the local reference system of each wall. From these solutions, we obtain the scaled 3D layout where the camera location, room height, and walls location is computed in meters. Presented our pipeline, we compare our method with others from the state-of-the-art. However, this comparison is not completely fair. On one hand, the pre-information of each method is different. State-of-the-art methods use extra measures to compute the 3D layout, while we only rely on the image information. On the other hand, the dataset used to compute the metrics are different, since there is no public dataset for non-central panoramas. Nevertheless, the comparison base shows that our method outperforms the state-of-the-art in most of the metrics by a margin. As qualitative demonstration, we show different examples of scaled layout reconstruction from our method in virtual environments. The green wireframe shows the real layout in meters, while the reconstruction is made with our pipeline without extra measurements. Thank you all for your time.